Welcome to the next video. Now we're going to be looking at redox reactions, and this is one that we may have discussed a bit already or that you've seen in some of your prior chemistry courses, where a redox reaction or an oxidation reduction reaction shows a movement of electrons. And this is really important because the next topic we're going to be looking at is electrochemistry. Basically how we can take a redox reaction and harness that flow of electrons, right? If we have electrons that are moving from one species to the next, maybe there's some way, there is, where we can channel the flow of those electrons to get a useful amount of chemical work, right? Because this is pretty much how a battery works, where we have a reaction that if it's allowed to proceed, we have a flow of electrons that powers, any of your devices that you could possibly want. And that's a very useful thing and relevant in today's society. So first things first, though, we need to understand these reactions, these oxidation reduction reactions. And so this may be a bit more of a refresher, but will be very important to know all parts of these redox reactions if you're going to understand how the electrochemistry works properly. And with that, let's go ahead and jump into the video. When we're looking at an oxidation reduction reaction or a redox reaction, what's important to realize is what we're looking at is electron transfers. And as we study oxidation numbers here in the coming slides, what we're going to see is that this is what's useful because it shows where the electrons are leaving and therefore where they're going to. So this is a pretty straightforward redox reaction here that's not balanced, but still will show how the electrons move. And we have silver that's positive and copper that has a charge of 0 that's become silver that's solid and copper with a charge of 2+, because that is a charge that copper likes to take. So what we see here is that one of the species, namely the copper, is being oxidized. It's losing electrons. It's going from a charge of 0 to a charge of 2+. And because the electrons are negative, what this means is that 2 electrons are produced when copper loses 2 electrons. And we can show this as a half reaction with those electrons as products with respect to just the copper. Reduction is the gain of electrons. So in this case, the silver plus ion is being reduced, which is a bit confusing to think about because it's actually gaining electrons. But because the electrons are negatively charged, this reduction more specifically refers to the charge or oxidation number of the species. So it's going from +1 to 0, which is a reduction in value. These half reactions are put together into the balanced chemical reaction that we could see above, although it's not actually balanced. But what's important to note is that when we have a reduction, there must be an oxidation. Electrons don't just come from nowhere, and they don't just get to something from anywhere, right? They have to come from somewhere and go somewhere else. So in this case, it's the copper that's supplying the electrons, which are going to the silver. And if you can appreciate these half reduction reactions or these half reactions, we can appreciate that a redox reaction shows this flow of electrons. Okay, another thing we want to refer to is the oxidizing agent and the reducing agent. Because as we mentioned, there must be an oxidation for a reduction and vice versa. So what we'll say is that the oxidizing agent is what promotes oxidation by being reduced. And the reducing agent is going to promote reduction by being oxidized. In other words, the species that's reduced is the silver plus, so it is the oxidizing agent because it causes the copper to become oxidized, and therefore the copper is the reducing agent because it makes the silver plus reduced. So a bit confusing nomenclature, but something that is important to keep in mind when studying these electron transfer reactions. Another thing we want to do is we want to keep track of oxidation numbers, because while we were dealing with cations previously, these redox reactions are also common when it comes to molecular species where we don't actually have ions and separation of charge in that way. So the way we look at oxidation numbers is basically we assume that for all the polar covalent bonds, let's just assume that they're fully ionic. And what's important to point out here is that this is a bookkeeping method. This is not an actual charge. We are basically crediting the electronegative atom as having the electrons. But as we know from our study of polar covalent bonds, it's not the same as a full separation of charge. In other words, if we have HF, this has a partial negative charge on fluorine and a partial positive charge on hydrogen, and it has a net dipole. With this idea of oxidation number, we say, well, let's just say that the electrons are in a whole number on one or the other. And let's just say that hydrogen has an oxidation number of +1 and fluorine has an oxidation number of -1. Now again, these are not charges and it's not exactly like this, but by having some rules about oxidation numbers, we can see what species are going to lose electrons and what species are going to gain electrons. So here's some other rules of oxidation numbers. These are generally in textbooks, anyone you choose. This is from OpenStax. And what I think is most important is the following, especially number 4 here, which I've outlined. First of all, if we look at rule number 1, if we have an atom in an elemental substance, the oxidation number is 0. And if it's in a monatomic ion, this is rule number 2, it's equal to the ion's charge. Basically, what else could it be, right? If the substance has a charge of 0 overall, the oxidation number of the atom all by itself must be 0. And if it's something like O2, then they're both going to be 0. When we have hydrogen, oxygen, and halogens, these, when they're combined with something other than themselves, so if it's H2 or O2, that's elemental state hydrogen and oxygen, and the oxidation number would be 0. But if it's water, H2O, that would be hydrogen +1, oxygen -2, and therefore it would have a neutral overall charge because there's 2 hydrogens. And that's this rule 4, which again is the most important, I think, for figuring out what the oxidation numbers are, because if we adhere to rule 4, which is to say that all of the oxidation numbers need to add up to the charge on the molecule or ion, it's kind of like rules 1 and 2, what else could they be? And when we know that certain atoms like to have certain oxidation numbers, we fill in the rest based on what the overall oxidation numbers need to sum to. So in other words, if hydrogen likes to be +1, oxygen likes to be -2, again in compounds, not when they're in their elemental state, and halogens like to be -1, we can use rule 4 to find the oxidation number for other atoms. And remember that rule 4 doesn't just apply to the overall species, it applies to the polyatomic ions that may exist within that species as well. Okay, so let's get started here with one like this. What is the oxidation number of chlorine in this species? And while I did just say that halogens like to be -1, this is a bit of an exception to that case. Chlorine is not going to be -1 here, though it will very commonly take a -1 charge. Use what oxidation number we know oxygen and hydrogen like to be to figure out chlorine. So go ahead and pause the video here and see if you can figure this one out. All right, hopefully you're able to come to an answer. The answer here is indeed 3. So HClO2 is neutral. So overall, when we add up all the oxidation numbers, it's got to be 0. And the oxidation numbers are +1 for hydrogen. We don't know the chlorine, so we're going to call that X, and -2 for oxygen. We can literally set it up as an algebraic sum, solving for X, and we get +3, but there are many ways to kind of figure this out in your head as well. All right, let's try another one. What if we have 2 different carbon-containing species? Again, we want to use the hydrogen and oxygen, which we know like common oxidation numbers, to figure this one out. What is the oxidation number of carbon in CH4, which is called methane, and the oxidation number of carbon in carbon dioxide? All right, hopefully you were able to come to an answer here. The answer is -4 and +4. So we know that hydrogen likes to be +1. So in CH4, there's 4 of them. That means it contributes +4, and therefore the carbon must be -4. In CO2, oxygen likes to be -2, and there's 2 of them. So that's -4 from the oxygens, and therefore the carbon must be +4 in that case. Now, this is a great example because a lot of times we'll have 2 carbon-containing species, one is a reactant and one is a product, and methane, if burned, will form CO2 as a byproduct. So if we have that occurring, what we see is that carbon is losing electrons. It's going from -4 to +4, and therefore we would be able to conclude that it would be oxidized if it's going from CH4 to CO2. All right, let's take a look at another example of something that we may come across in our study of redox reactions. And I'm going to go ahead and leave this one here. Go ahead and pause this and see if you can get an answer. What are all the oxidation numbers here to start? We're trying to say, is it a redox reaction? And if we determine all the oxidation numbers, we should be able to figure this out a bit further. Because if it's a redox reaction, that means the oxidation numbers of some atoms must be changing. One must be getting higher and one must be getting lower. Oxidation and reduction always happen with each other. If they're all the same on both sides, then we would conclude that it is not a redox reaction. So that's my best hint for you to get started. And also remember that when we're looking at something like sulfate, that one always has a charge of -2. That's what's here, SO4. This is sulfate, SO4 2-. So when we're supposing and figuring out the oxidation numbers for sulfate, we can base that off of the -2 overall. All right, hopefully you have paused the video and figured out some of these oxidation numbers. I'm going to go ahead and reveal them now. Here are all the oxidation numbers for the species. So aluminum on the reactant side has an oxidation number of 0 because it's all by itself. In H2SO4, we know that hydrogen likes to be +1, oxygen likes to be -2, so sulfur must be +6. In the product side, all the way at the end, H2, this is elemental hydrogen, so it's not hydrogen that likes to be +1, it's going to be hydrogen of oxidation number 0. And we can see that this is actually an ionic compound for Al2SO4 here, aluminum sulfate, and aluminum likes to be +3. That's reflected in the charge for the 3 sulfates as well. 3 sulfates will give a -6 charge, so the aluminum must have +3 because it's split between the 2 aluminums. So again, this is a great practice. Getting all the oxidation numbers is essential, and now we want to interpret the results because we see that there are actually oxidation numbers changing. And what are they? Well, the aluminum is going from 0 to +3, so the aluminum is being oxidized. Hydrogen is going from +1 to 0, and sulfate is actually staying the same, so that one's not being oxidized or reduced here. But because we see that aluminum is increasing in oxidation number, it's oxidized. And hydrogen is decreasing in oxidation number, so it's reduced. Therefore, what we can conclude is that the electrons are going from the aluminum to the hydrogen, and yes, this is a redox reaction. What about the following? In the following redox reaction, which element is being reduced? So again, it's good to use that method that we did previously where we calculate all the oxidation numbers for all the atoms on the reactant and product side. The one that's reduced will be the element that is decreasing in oxidation number, and therefore we'll be able to conclude what's being reduced, what's being oxidized, and where the electrons are going from and to. All right, I'm going to go ahead and reveal the oxidation numbers and the answer here. So as we look at this one, lead oxide, we know oxygen likes to be -2, so therefore lead must be +2. Same deal for carbon monoxide, CO. And on the other side, we have lead in the elemental state and CO2, which has a +4 oxidation number on the carbon, and we've already discussed that. So what we see here is that lead is going from +2 to 0, and carbon is going from +2 to +4. Therefore, lead is being reduced, and carbon is being oxidized, and therefore lead is the answer to this question. All right, how about one more? Hopefully this is getting to be a bit more straightforward by now, but again, what we want to do is get all of these oxidation numbers and then conclude about the reaction, what's being oxidized, and take it from there. All right, I'm going to go ahead and show the oxidation numbers and the answer, so make sure that you have something written down, otherwise perhaps be sure to pause here. But anyway, we're looking at H2SO4 plus NaOH goes to Na2SO4 and water, and we get all of the oxidation numbers shown here. And these should be all pretty accurate. There isn't really much ambiguity in calculating the oxidation number, so if you're not getting the right ones, remember that oxygen likes to be -2 in a compound, hydrogen likes to be +1. Recall some of the fundamentals of ionic compounds as well, because that can help you get the charge, which if it actually has a charge, then that's also going to be its oxidation number. But again, you know, oxygen in water doesn't actually have a charge. We're just formally attributing those electrons to the oxygen. But anyway, what we see in this one is that actually all the oxidation numbers are exactly the same, and therefore there are no movement of electrons from one element to another in this reaction. This is actually an acid-base reaction. We've seen these before, and as a result, there is no change in any oxidation numbers. What we have moving around instead are the protons. So not every reaction is going to be a redox reaction, and by getting these oxidation numbers, we'll be able to determine which ones are redox reactions and which ones are other types of reactions, such as this acid-base reaction shown here. All right, that is redox reactions. We will be using what we've learned here when discussing electrochemistry in the next chapter very soon.